So today we are going to talk about limits and continuity by Arnab Roy. Now what are limits? Limits are built upon the concept of infinitesimal. Instead of evaluating a function at a certain x value, limits ask the question what value does a function approaches as its input and a constant becomes infinitesimally small. Notice how this question does not depend upon what FC actually is. The notations for writing a limit as x approaches a constant of the function fx is limit x tends to c fx is equal to L, where c is the constant and L, if it is defined, is the value what the function approaches to. Evaluating the limits direct substitution. Sometimes the limit as x approaches c of fx is equal to fc. If this is the case, just directly substitute in c for x in the limit expression as shown below. Limit x tends to c where fx is equal to fc. You can see that from the picture given in the right hand side. Now dividing out the technique, always start by seeing if the substitution method works. If when you do so, the new expression obtains an indeterminate form such as 0 by 0, trying the dividing out technique. Because both the numerator and the denominator are 0, you know that they share a similar factor. Factor whatever you can in the given function. But if there is a matching factor in the numerator and the denominator, you can cross through them since they won out. With your new simplified function, attempt the substitution method again. Plug whatever value x is approaching in for x. The answer you arrive at is the limit. Note, you may need to algebraically manipulate the function. Two examples of limit are given here in the right hand side. It says limit x tends to 5 x minus 5 divided by x square minus 25, which is equal to limit x tends to 5 x minus 5 divided by x plus 5 into x minus 5, which means limit x tends to 5 1 divided by x plus 5, which means 1 by 10. And the other one says limit x tends to minus 3 x square plus x minus 6 divided by x square minus 9, which means limit x tends to 3 x plus 3 into x minus 2 divided by x plus 3 into x minus 3, which gives limit x tends to minus 3 x minus 2 divided by x minus 3, which is equal to minus 5 divided by minus 6, which gives the result 5 minus 6. Now let's come to rationalizing. Sometimes you will come across the limits with radicals in fractions. The steps are: use direct substitution by plugging in 0 for x. If you arrive at an undefined answer 0 in the denominator, see if there are any obvious factors you could divide out. If there are none, you can try to rationalize either the numerator or the denominator by multiplying the expression with a special form of 1. Limit x tends to 0 root over x plus 1 minus 1 divided by x. By rationalizing this, we get limit x tends to 0 root over x plus 1 minus 1 divided by x into root over x plus 1 divided by root over x plus 1 plus 1. So simply the expression, then evaluate the rewritten limit. So after doing this, limit x tends to 0 x plus 1 minus 1 divided by root over x plus 1 gives 1 divided by 2. So the example was limit x tends to 0 x divided by x into root over x plus 1, which is equal to limit x tends to 0 1 divided by root over x plus 1. Now what is the squeeze theorem? The squeeze theorem states that if hx is less than equal to fx, which is less than equal to gx, and limit x tends to c, hs is equal to limit x tends to c, gx is equal to L, the limit x tends to c, fx is equal to L as proved from the graph. Now let's learn some special trig limits, and we need to memorize this as well. Cos h divided by 2 less than equal to h divided by 2, which is less than equal to tan h divided by 2. Here h is an angle in the radians, area of blue cos h sin h divided by 2, and the area of pink is h divided by 2, and the area of yellow is tan h divided by 2. The above equation means 1 divided by cos h, which is greater than equal to sin h divided by h, which is further greater than equal to cos h. Now since limit h tends to 0, 1 by cos h is equal to limit h tends to 0 cos h is equal to 1. By the squeeze theorem we can say that limit h tends to 0 sin h divided by h is 1. Now limit h tends to 0, 1 minus cos h divided by h is equal to limit h tends to 0, 1 minus cos h divided by h into 1 plus cos h divided by 1 plus cos h, which means limit h tends to 0 where 1 minus cos square h divided by 1 plus cos h is equal to limit h tends to 0 sin square h divided by 1 plus cos h is equal to 0. Now what is continuity and discontinuity? A function is a continuous in the interval ab if there does not exist a c in the interval ab such that fc is undefined or limit x tends to c minus fx not equal to limit x tends to c plus fx or 3. The following functions are discontinuous. B and C did not fulfill all the properties of continuity as defined above, as shown in the 4 figures below. Removal versus the non-removal discontinuities. A removal discontinuity exists at C if f can be made continuous by redefining fc. If there is a removal discontinuity at C, the limit as x tends to C exists. Likewise, if there is a non-removable discontinuity at C, the limit as x tends to C does not exist. For this function, there is a non-removable discontinuity at x equals to 3, even if f3. For this function, there is a removable discontinuity at x equals to 3. Now, f3 is equal to 4 can simply be redefined as f3 is equal to 2 to make the function continuous. The limit as x tends to 3 exists is redefined. The function will never be continuous. The limit as x tends to 3 does not exist. You can see from the graph given in the left hand side. Now, what is intermediate value theorem? The intermediate value theorem states that if x is a continuous in the closed interval ab and if a is less than equal to m less than equal to fb, then at least one c exists in the interval ab such that c is equal to m as shown in the graph. Now one question comes into our mind: when do the limit not exist? If limit x tends to c minus fx not equal to limit x tends to c plus fx, then limit x tends to c fx is equal to undefined, as shown in the figure below. Limit x tends to c fx divided by gx is equal to undefined. There is an asymptote at x equals to c for fx divided by gx. Now what are vertical asymptotes? Fx and gx are continuous on an open interval containing c. If fc is not equal to 0 and gc is equal to 0 and there is an open interval with c which gx is not 0 for all the values of x that are not c, then let b and c be the real numbers and n be a positive integer. F and g be the functions with the following limits. Limit x tends to c fx is equal to L and limit x tends to c gx is equal to k. Now the sum or the difference limit x tends to c fx plus minus gx is equal to L plus minus k, and the quotient remains as limit x tends to c fx divided by gx, which is equal to L divided by k. Now in the scalar multiple, limit x tends to c b fx is equal to bl, and the product limit x tends to c fx to the power n is equal to L to the power n. Now the product comes as limit x tends to c fx into gx is equal to L into k, which is Lk. What is limit substitution? With the limit substitution informally named so by yours truly, if limit x tends to c fx is equal to L, then limit x tends to c gfx is equal to limit f tends to L gfx. This is useful for evaluating the limits such as limit x tends to c sin 2x divided by x. How do limits relate to the derivatives? What is a derivative? The derivative of a function is defined as that function instant rate of change. Applying prior knowledge as learned in the pre-algebra, the rate of change of a function is delta y by delta x. Defined by applied knowledge of limits. Consider that a limit describes the behavior of a function as x gets closer and closer to a point on a function from both left and right. Delta y by delta x describes the function's rate of change. To find the function's instant rate of change, we can use limits. We can write limit delta x tends to 0, delta y by delta x. Y as the change in x gets closer and closer to 0, we can more accurately predict the function's instant rate of change and thus the function's derivative. Consider that delta y by delta x can be rewritten as y2 minus y1 divided by delta x. X plus delta x, comma, fx plus delta x. Analyze the graph. Notice that the change in y between any 2 points on a function is fx plus delta x minus fx. Thus, delta y by delta x is equal to y2 minus y1 divided by delta x, which is equal to fx plus delta x minus fx divided by delta x. So, limit delta x tends to 0, delta v divided by delta x can be rewritten as limit delta x tends to 0, fx plus delta x minus fx divided by delta x. Therefore, the derivative of fx at x is given by limit delta x. Therefore, the derivative of fx at x is given by limit delta x tends to 0, fx plus delta x minus fx divided by delta x. I hope you all have understood.